Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. Today's lecture is entitled the AND logic function. Okay, so the AND logic function has a distinctive shape symbol, just like that. We've already gone over the basic performance of the AND gate. We're going to go into this a little bit more in detail. The truth table is right here. Okay, so first off, what is the rectangular block symbol, just in case you ever run across this? Appropriately enough, it's got the AND symbol. It's got inputs, any number of inputs. Right now we're sticking to 2 inputs, and that's its output. Exact same thing, just different format. What is the behavior of an AND gate? Its output high only when all inputs are high. The truth table for a 2-input AND gate is right there. And I'm going to redraw that right here, illustrating every other, every 2. Okay, I'm getting all possible combinations of that. 0 ANDed with a 0 is a 0. 0 ANDed with a 1 is a 0. 1 ANDed with a 0 is a 0. 1 ANDed with a 1 is the one and only time because all inputs have a high. Okay? That's for 2 inputs. How do we do this with 3 inputs? Because there is such a thing as a 3-input AND gate. A, B, and C. Let's say our output is X. Okay, so how are we going to do this? Come up with all possible combinations of inputs. And notice I'm going A, B, and C. I could just as easily C, B, A. It doesn't matter the order of the inputs because this is combinational logic. Okay, we'll go into sequential logic. It doesn't matter the order that these inputs come in. It will always perform the AND function. Okay, so I could write it forward, I could write it backwards. I don't have to call them A, B, or C either. I could call them banana, crocodile, banana tree. It doesn't matter the name of these things. That's just I'm assigning them a signal. So let's do every other. 0, 1, 0, 1, 0, 1, 0, 1. Every 2, 0, 0, 1, 1, 0, 0, 1, 1. Every 4, 0, 0, 0, 0. 1, 1, 1, 1. That is a trick for me to remember what are all possible combinations. And again, staying organized is absolutely key to your essential to your success in digital electronics. You have to exhaust all possible combinations of inputs. Let's say you forget a combination of inputs and you don't know how your truth table works because you're skipping that one particular section. Additionally, notice and we're going to go into Boolean numbers, binary numbers in a little bit here. How many possible combinations of one input can I have? Well, from our NOT gate, we have 2. How many possible combinations of, so here's number of ins, number of combos. Now I have 2 inputs. I've got 4 possible combinations of inputs. Now I've got 3 possible combinations of inputs. 3 inputs. What's my number of possible combinations? 8. Do you see the pattern? What's going on here? 4. Maybe there's 16. So the number of inputs, the number of combos you can get is 2 to the number of ins. Okay? We'll go into this. I kind of want to stick to, lucky you, 2 input gates right now. I'm just kind of introducing this thing up front here. Okay, but while I've got this nice beautiful truth table to our left here. What is the input and output? What is the output of a 3-input AND gate? When the output is high, when all inputs are high. What is the one and only time in our 3-input AND gate where all inputs are high? Right there. 1. All the rest are zeros. Also helps to give yourself a dividing line every 4, just to, because After 4, my eyes kind of glaze over. Okay, so that is just something we're going to be dealing with a little bit later. Multiple beyond 2 input gates. Let me clean this up. Okay, so before we go into some of the timing diagrams here, let's stick with this truth table. If you ever see the expression in a text or in a program, the output X, A and B, kind of like multiplication. It's logical multiplication, not exactly the same, but think about it. 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1. Okay? You can shortcut that. I know what you're talking about. AB. I know there is a multiplication sign, an and sign in there. In VHDL, the programming language that we'll be using, our output X is assigned A and B. Okay? Additionally, you'll notice when you start programming, there are key words. When you type the word and, it becomes bold. Okay, these are keywords that cannot be used as a variable. You can't call a variable and because it's a key word, it's reserved. Okay? Semicolon to close that. You'd use that expression to program in VHDL an AND gate. You would tell that programmable logic device, I want this signal to be ANDed with the other. Let's go into a timing diagram. Using this truth table right there, what is the output when A and B have signals on them? Okay, as opposed to our static truth table where we're constantly having a 0 or constantly having a 1 on our inputs. Now our input is changing. Like I said earlier, these gates, as long as they're powered up, go to work every single day, and they're constantly ANDing its inputs. Okay, so let's go ahead and pretend A looks like this, and B looks like this. It's digital data, and just simply assign the truth table, assign the output, the value for the truth table at every single moment this is true. And what we're going to do is we're just going to walk across our truth table in this direction. Okay, so the first from time, let's call that time 0 to 1, 2, 3, and 4. Okay, so from time 0 to 1, both A and B are 0. Look at your truth table. When they're both 0, our output is 0. From time 1 to 2, A is 0, B is 1. Where are we at the truth table? Right there. Our output is also 0. Now we are at another spot on our truth table from time 2 to 3. Right there. Finally, we get a value from 3 to 4 where both inputs, A and B, are 1. What is our output? The output is high only when all inputs are high. Okay? So all the timing diagram is the application of that truth table on an ongoing time basis. Okay, let's get slightly more complicated here. Looks like A's got some random non-periodic information on it, and B's got some 2 pulses on it. Go ahead and see if you can perform the output of this, the expected output of this timing diagram, to see if you are going to match exactly what I do here. So go ahead and pause the recording and go ahead and try this and see what you match. I'll be here waiting for you. Okay, so hopefully you've paused and you've come up with something similar to what we've just done. Okay, notice to have taken away one of your handy dandy little pieces of equipment, i.e. the truth table. It helps when you're doing these timing analyses to actually have the truth table with you. If you don't want to carry truth tables around with you all day, just remember the expression. An AND gate, the output is high only when all inputs are high. So I can shortcut a lot of these things. You can do that whole walking from time 0 to time end of time It's far easier to just use that expression. Its output is high only when all inputs are high. When are the times both inputs are high? Right there, and right there. So what does our output look like? 0, brief pulse, 0, brief pulse, whole bunch of zeros, 1 at the very end. Okay, so it's a shortcut. If you're using just that expression there, you can just walk through the magic times, those times when both or all input signals have a 1 on it. Okay, so let's try this example. Slightly more complicated again. I've got 2 AND gates now. Okay, and you're going to see this a lot. It is a single signal, say that 10 times fast, being applied to 2 different inputs for 2 different gates. And I have not completed the schematic, by the way. Look at gate 1, which is this guy, has inputs A1 and B1 and output X1. And the gate 2 below it has inputs A2 and B2 and outputs X2. What if I was to take the single signal in red there and apply it to both of the A inputs? What would that look like schematically? What I would do is I'd have that thing going there, that going there. And that is that signal in red, which it looks like basically what I've already drawn in red. Okay, so that's, I'm just going to say that that is that signal, digital data, being applied to A. Okay, notice very similar to our basic electronics series, that indicator right here, that is a connected wire. B1 and B2 for gate 1, B1, let's tie it to its crossing. You know, it's not connected to that wire. Plus 5 volts. B2, let's provide it a ground, so i.e. a logical 0. Okay, go ahead and see what you think that these timing diagrams would look like for the outputs X1 and X2 respectively. Okay, go ahead and pause the recording. Go ahead and see what you come up with. And again, put the input B1 on the timing diagram. Put the output X1 on the timing diagram. Same thing for B2 and X2. Okay, hopefully you paused it and you came up with something similar to this. What does B1's input look like? It is being provided a logical high. It is constantly high. What does the input B2 look like? It is being provided 0 volts, a logical low. It looks like this. Now perform the analysis of gate 1. The output is high for an AND gate only when all inputs are high. What it's going to look like, when is it high? When A1 is high? B1's always high. It's always high for gate 1. So I'm going to have a high when A1 is high. What does my X1 waveform look like? Exactly like A1. I could even write it in red if I wanted to. If you could think about that. If waveform A1 was colored red, it would come out red. What this is illustrating is an essential Boolean property of the AND gate. Input A ANDed with 1. Think about multiplication. If you're constantly multiplying something by 1, what do you get? That's something. It makes sense. It's just like multiplication. Let's do the opposite here. B2, gate 2. Its output is high only when all inputs are high. Yeah, A2 has all these inputs high. Look at B2. It's never high. What is the output for an AND gate? Output is high only when all inputs are high. Well, if B2, one of its inputs, is never high, it will never have an output. So our output X2, total flat line on 0. So what does that illustrate? Well, it illustrates an essential Boolean property also. A, i.e. a digital data waveform, it doesn't have to be A, it could be called whatever, ANDed with a constant 0. Anytime you AND something with a constant 0, it's kind of like you're multiplying something by 0. You always get a 0. So this is a really cool application of an AND gate. We're already getting to our first applications here. What about using an AND gate as a gatekeeper? As basically you enable something, you turn something on or turn something off. What are you turning on or off? You're turning incoming data on or off. Okay, think about this. AND gate, here's my output. Here is some incoming digital data stream. It could be from some sensor or whatever. Here is my enable pulse. When an enable is 1, I'm sending that same data to the output. When enable is 0, what am I sending to the output? Straight zeros. Okay, so that's pretty cool. An AND gate can be used as almost like a gatekeeper. Okay, so here's a couple challenge problems here for timing diagrams. If you really know what's going on with an AND gate, you should be able to figure this out. And I'm not going to give you the answer for this particular one until next week, or next week. Look at gate X1. I'm applying input A to its, and which by the way is a digital data stream, to that input and that input. What does the output X1 look like? Think about it. Now, applying waveform A to this guy's X2 input. Very tricky. I'm applying not A to the second input. Okay? Think about it. Okay, we'll come back to these here a little bit more challenging. Okay, let's go ahead and look at some of the schematics in the pinout diagram for the 7408, which is the quad 2 input AND gate TTL chip. Okay, quad. Why? Because there's 4 of them. 1, 2, 3, and 4. If you ever see on a chip, on a schematic, when you see 1/4 7408, and there's like a box with a U on it with a number after there, what's implying is I'm using one AND gate on a 7408. And this is a cool, and the U, I don't know why, it's just U is the chip. You know, like how many chips do you have? U1 through 50, okay? That U number, let's pretend that you only have one chip. It's a U1, okay? The reason why you use that fractional notation, it's for when you're designing a circuit. When you say, okay, you're using 1/4 of a 7408, and another portion in the circuit you have to use another 1/4 of a 7408, and another portion of the circuit you have to use 1/2 of a 7408. How many 7408s do you need? You need 1. Okay, it's just it's a means of getting all your parts ready. So anytime you see that fractional notation, so for example, the hex inverter, when you see 1/6 7408, how many NOT gates are you using? You're using 1. Okay, just a brief notation. Brief comment about notation in schematics. The 7408 has, as like it says, 4 input, 4 2-input AND gates. Looking at gate 1, that is our 1A input. Here's our 1B input. Here's our 1Y input, respectively on pins 1, 2, and 3. Gate 2, its inputs are pins 4 and 5, and its output is 6. Okay, we'll be looking at the schematics, the data sheets in lab. But if you got some time, go ahead and go to alldatasheets.com and pull up a data sheet for the 7408. Again, critical to your understanding, critical to functioning of your circuits. You have to have 5 volts on VCC and ground on ground. One thing I failed to mention in our timing diagram discussions is you may have an input A, it's a digital data stream, on input A. What if you have nothing on input B? So we talked about a constant high or a constant low. What is an open being read for a TTL circuit? Is being read as a 0 or is it being read as a 1? Your output conditions will change based upon how it's reading an open. Okay, critical to your understanding of you can't just leave these things dangling to expect the functionality of these things to stay the same. You'll be doing that in lab. Mentioned the data sheet. We talked about the writing these things out and timing diagrams. How is the AND gate applied? It's a pretty cool gate, and you may have seen this diagram before in motor controls. This is really the major purpose behind digital electronics. Besides doing all the whiz-bang stuff with computers and memory and stuff like that, it is essential to your understanding of motor controls and PLCs. The AND gate is what's known as a permissive, a safety chain. Okay, condition A, logic. contact A, it's a switch, it's a sensor, whatever, that may be closed, but to get this motor to run, or whatever it is there, B must also be closed. It's a safety chain. It's checking to make sure that everything is okay to run. Both conditions must simultaneously be true. Any one of them can turn the motor off. For example, you want there to be a sufficient amount of pressure, sufficient amount of fuel. It has to be within a certain operating temperature range. You can have a number of different permissives in that safety chain. For example, and we're going to do a whole lecture on digital logic as applies to motor controls and PLCs. Here's our line 1, our hot, and line 2, ground. So this condition A, B, and C, is there enough pressure? Yes, there is. It closes. Is the engine within operating temperatures? Yes, it is. Is there enough fuel? Nope. Okay, so my rocket ship is not going to blast off. Okay, now there is enough fuel, blast off. That thing lights up. So it's a safety chain. Additionally, like I said earlier, is any one of those conditions can turn it off. So A, B, and C, can't remember what the earlier one was. Pressure, fuel, all set, and temperature. All of a sudden the motor overheats, turns the whole thing off. Okay, so you need all of them to turn it on. Any one of them can turn it off. Okay, so it's a safety chain, permissive. Very similar to that is that concept of any one of them can turn it off. What if you want an alarm? Let's go back to our sourcing and sinking arrangements. Let's do a sinking arrangement for an AND gate. Current control resistor plus 5 volts. That is a sinking arrangement, A and B. When does the light up? Okay, you want to know if condition A or B is not true. You want to know if there's, let's say that's a pressure, there's not enough pressure, and that's temperature. So A, B, your truth table, our output X, same truth table, but because it's a sourcing relationship, a sinking relationship, what lights the LED? A 0. Boom. It tells you that little LED. You don't have to put it to an LED. You put it to an alarm. Some audible alarm. It goes off when any of those conditions, A or B, are false. There's not enough pressure. There's not enough temperature, or there's not enough pressure or not enough temperature. Okay, so those zeros are just as important as the ones in logical circuits. It doesn't always have to be a sourcing relationship. We've got a sinking relationship here, which allows us to perform some indication when one of those conditions are not true. Okay, so that's a pretty cool application of a sinking circuit. And here's the same circuit done in a sourcing arrangement. That LED now can signify some motor contactor. Go ahead and motor coil. Go ahead and start that thing up. So when there's enough pressure and when there's appropriate temperature, when does that LED light up? When there's enough pressure and there's enough temperature. Okay, appropriate temperature. That concept of sinking and sourcing is not limited to the NAND gate, the NOT gate. All that does is it inverts things. So you may want to have a sourcing output for an AND gate or a sinking output for an AND gate. Last but not least, let's talk about one other application. We already talked about kind of the gatekeeper / enable ability of an AND gate. There are these concepts in computers called masking. Okay, let's say you've got an 8-bit binary number. So there are spaces, there's 8 spaces into which you put numbers. 0, 1, 2, 3, 4, 5, 6, and 7. And let's say only these guys have important data. You want to mask, you want to get rid of what's in 0, 1, 2, and 3. How do you do that? Think of our gatekeeper strategy. Let's have 8 AND gates. I'm going to go ahead and draw that. Take the outputs of those registers 0 through 7, assign to one of the inputs of the AND gate, and we're going to go ahead and we want to erase 0, 1, 2, and 3, but leave what's in 4, 5, 6, and 7. How do we erase something with an AND gate? Put a 0 on that one's input, 0 on that one's input, 0. So those are all two independent AND gates. Put 0 volts right there. Put a logical 1 on there, or 5 volts on that one. So what do we get in this section? It's 0 and whatever. Always equals 0. What do we get in this section? It's 1 and whatever. Always equals whatever. So that's what's known as a mask. I can partially remove the contents of a register and keep the important stuff. Okay, so the AND logic function, we went into it a little bit more in detail here. Hopefully we did this with more efficiency than our previous NOT logic function. I had a bunch of things to introduce there all at once, so sorry if that was a little bit longer. Let's go ahead and move on to the OR logic function.